Assalamualaikum and hi everyone. In this video, we will present report about experiment 2, single stage compressor. We are from group 2, consists of Umar Irfan bin Zulkifli, Muhammad Azhan bin Abdullah and myself Nurul Afifah Binti Zulkifli. Compressor is a device used to increase the pressure of compressible fluid, gas or vapor. It can be by reducing the fluid-specific volume during passage of the fluid through compressor. One of the usage compressor is to compress fluid then deliver it to a higher pressure than its original pressure. Open system process has mass crossing its boundary as the process occurs. Compressor is one of the examples of an open system that can operate at a steady state. This experiment of single-stage compressor that related with energy balance and shows the working principles of a compressor, including heat loss from the compressor. When the power and motor is switched on, the temperature of the outlet air is recorded until two consecutive readings at the same temperature. The consecutive readings are obtained at 28 and 29 minutes, which is 149 degrees C. The graph plotted in order to analyze the heating curve and behavior of single-stage compressor. The outlet temperature of the compressor will increase exponentially with time after analyzing the data obtained throughout the experiment. For introduction, in this experiment, we will measure the rate at which a single-stage compressor heats up and the rate at which its losses heat at a steady state. A single-stage compressor compresses and pressurizes air to transform power, often from an electric motor, a diesel engine, or a gasoline engine, into kinetic energy. Lower pressure frequently employed. An objective for this experiment is to evaluate how quickly a single-stage compressor heats up and to analyze the steady-state heat loss of a single-stage compressor. For theory in this experiment, in a typical single-stage vane compressor, an offset rotor drives two sliding vanes, trapping a fixed volume of air between them. The outlet, where the area and hence volume is reduced, receives this amount of air and push it out. As a result, its pressure is increased and it is forced out of the outlet port. This is the formula that we use to calculate the specific volume through flow meter, volumetric flow rate, mass flow rate, energy added to air by compressor, power out of motor, and heat emitted from compressor.
The next slide is apparatus. Single-stage compressor consists of two air chambers, inlet valve, outlet valve, airflow meter, pressure reader for atmospheric pressure, tachometer, stopwatch, compressor, motor, spring balance, and meter for temperature reading. Next, we continue with the methodology, which is the procedure. First, the power switch was turned on. Second, the green inlet valve was fully open. The valve was turned anti-clockwise to open it. Third, initial reading for all parameters were recorded in table 1 at the beginning of the experiment. The tachometer is used to record the motor speed. 4. The motor switch was turned on. 5. The compressor outlet pressure P2 was set to 1 bar gauge using the red outlet valve. The valve is turned clockwise to increase pressure. 6. The spring balance was adjusted to ensure that the indicator on the motor is between the two black lines prior, before recording any motor force value. 7. The temperature of the outlet air T2 was recorded at 1 minute interval using stopwatch until two consecutive readings are the same, which is less than 0.5%. Okay, to stop the experiment, first, The red valve is used to reduce the compressor outlet pressure to 0 bar gauge. The valve is turned anti-clockwise to decrease pressure. Second, the motor switch was turned off. Third, the power switch was turned off. So, we continue with the result. Okay, first of all, we plot the outlet temperature T2 over time, which is the data from the table 2, heating curve. The graph is on the right at the top on the slide. We also has labeled the graph with the title as you can see on the slide. For the y-axis, we use for outlet temperature T2, and the x-axis is the time from 0 to 29 minutes. From the graph, we found that the graph is slightly curved. Next, this is the calculation to plot the energy added to air by compressor and heat emitted from the compressor against time respectively. First of all, specific volume through flow meter. The formula is V0 equal to RT0 over P0, with R equal to 0.287 kilojoule per kilogram Kelvin. The value for the V0 is 0.856944 meter cube per kilogram. Next, volumetric flow rate. The formula is V bar equal to V in per 60 multiplied by 10 with the power of 3. The value for the V bar is 0.004633 meter cube per second. Third, mass flow rate. The formula for mass flow rate is M equal to V bar over V0. The value for the mass flow rate is 0.005407 kg per second. 4. Energy added to air by compressor. The formula is Hc equal to mCp T2 minus T1. The value for the Hc is 217.3538 watt. 5. Power out of motor. The formula is Wm equal to N multiplied by F multiplied by L multiplied by 2 pi multiplied by 9.81 and divide by 60. The value for the Wm is 513.4369 watt. Lastly is heat emitted from compressor. The formula is Qc equal to Wm minus Hc. The value for the Qc is 296.0858 watt. Okay, this is the data from the experiment that we use. First is length of top arm, L equal to 0.2 meter. Next, compressor swept volume, Vcom equal to 267 cm3 per revolution. Lastly, specific heat capacity of air, Cp equal to 1005 joule per kilogram Kelvin. On the slide is also have table 1, which the list of parameter for the single stage compressor unit and its initial reading that we got from the experiment. Next is table 2, which is table for time, outlet temperature, the energy added to air by compressor, and heat emitted from the compressor. We get the outlet temperature after we run the experiment from 0 to 29 minutes. We get the value for energy added to air by compressor and heat emitted from the compressor using the formula provided. Okay, from the calculation of the Hc and Qc using the formula provided, we plot the graph for energy added to air by compressor, which is Hc against time. We can see that this graph on the bottom on the slide is slightly increased, like the graph for the outlet temperature against time. We also plot the graph for heat emitted from the compressor. which is QC against time. This graph on the left at the top is very different. The graph is slightly decreased as you can see on the slide.
Okay, now I will present about discussion. So, the first is shape of graph obtained in result 1, heating curve and related thermodynamic phenomena. According to the shape of the graph obtained in result 1, heating curve, the temperature of the compressor increases as time passes. This indicates the compressor is heating up. A fixed volume of air is trapped between two sliding vanes operated by an offset rotor as a result of the work input to air compressor. The air is finally driven out the outlet. The temperature of the outlet air was measured at 1 minute interval until it remained constant for 2 consecutive minutes, which occurred at minutes 28 and 29, which the highest temperature reading of 149 degrees Celsius. The second discussion is the energy that is being put into the system when the system is heated up. The energy hits the air, allowing the temperature to increase and stabilize at a certain point before it reaches thermal equilibrium. This illustrates that the energy inputted into the system is absorbed by the system and energy lost to the atmosphere in the form of heat. The third one is amount of energy lost as heat as compared to first, the work input to the compressor, second, the heat added to the air. As compared to the work input into the compressor, the amount of energy lost as heat was smaller. The energy lost as heat, on the other hand, is smaller as compared to the heat applied to the air. The heat generated by compressor QC was a heat loss in this experiment, while the energy applied to the air by compressor AC was the usable energy used to compress the air. The work input to the compressor was supplied by the motor's output power, which remained constant during the experiment. Energy cannot be created or destroyed according to the first law of thermodynamics. As a result, energy input was converted into heat released by the compressor and energy applied to the air in this experiment. When the temperature difference is higher, more energy is applied to the environment and lower the energy loss. According to the data, this means that the compressor was more efficient at a higher temperature. So, next is the safety procedures. First, start the compressor, letting the pressure gauge increase and the cut in, cut out pressure levels. Second, always operate as directed in the operator manual. Third, listen for any air leaks from all airlines or hoses. Do not continue if there are any leaks. Fourth, compressed air cleaning of machine parts must only be undertaken after all PPE and general workshop safety precaution has been observed. Fifth, never direct compressed air towards the body. So for conclusion, based on the experiment, the outlet temperature T2 gradually increased exponentially from 70 degrees Celsius initially until 149 degrees Celsius, but it remains constant after 28 minutes of heating. Steady state occurred at T equals to 28 minutes as the energy added by compressor and heat emitted from compressor remains at 646.6275 watt and negative 133.1879 watt respectively. During the heating process, the energy added to the air by compressor H also increases while the heat emitted from compressor Q decreases with time. It can be deduced that there are energy losses as the input energy is converted into heat and sound energy. The temperature will decrease by half if the compressor outlet pressure P2 is reduced from 1 bar to 0.5 bar, hence reducing the heat emitted from the compressor as well. The heating time could be longer while the shape of graph will be less steep. Lastly, this is all our reference being used for this experiment. I think this is all from us. Thank you.